Now that we have some tools for describing data, we can begin to discuss inferential statistics, which deals with how we can use data sets pulled as a sample of a population to make some hypotheses, test them, and then possibly apply those conclusions back to the population as a whole. In this video, let's discuss normal distributions and z-scores and percentiles. So first of all, what is meant by normal? What we're doing is describing in more technical detail something that you looked at in a previous section, which was a symmetric distribution of data. So we looked at curves that looked like this or like a bell curve, and we can now describe those as the normal distribution. Any data set that satisfies 4 criteria or most of 4 criteria is a good candidate to possibly have a normal distribution. All right, so some things to notice about this normal distribution. Most of the data values are clustered near the mean, and we have a single well-defined peak. All right, so if we look at the majority of the data, it's around the mean. We know that the mean is at the center for symmetric distributions, and we know that as we move away from the mean with a larger and larger deviation, the data becomes more rare. So you can see that the frequencies are lower to the left and to the right. Any sort of data that would be the result of a number of different factors would be a good candidate for a normal distribution. Anything that's a genetic type of data or affected by genetic and environmental factors would be a good candidate. Actually, test scores fit a normal distribution fairly well, and you might realize that that's because test scores are the factor of a number of different things. They don't necessarily just predict how much of the content you know. Test scores are affected by where you're sitting when you take the test, how much sleep you had, whether or not you studied, your preparation prior to joining a class. If somebody already knows a lot of the information, then and if it's review, then that affects the test scores as well. We also know that data that's pulled from a random sample is more likely to be normal than from a select sample. All right, so if we looked at heights of people, and if we look at just 4-year-olds, we may not necessarily have a normal distribution, whereas if we look at a random sample of an entire population of people, we would be more likely to have a normal distribution. Now let's talk about numerically where data is in this normal distribution. So we have a really convenient rule that lets us describe the percentage of data that's at various positions in relation to the mean. This is the 68, 95, 99.7 rule. And this rule says that about 68% of the values fall within one standard deviation of the mean. Okay, so here's the mean in the middle, and then from either one standard deviation below to one standard deviation above, that's where 68% of the data will fall. Because this is symmetric, we can split that in half, and we know that 34% of the data roughly is one standard deviation below the mean, and 34% is up to one standard deviation above. Next, we know that 95% of the values fall within 2 standard deviations of the mean. Right, so that includes the 68% within 1 standard deviation. All right, so if we wanted to know the percentage of people between 1 and 2 standard deviations from the mean, then we can take 95% and subtract 68%, right? And then we know 27% of the data values are in these 2 regions, and because this is symmetric, you can divide that in half, and we have 13.5% between 1 and 2 standard deviations above the mean, and 13.5% below. Okay, and then similarly, we know that 99.7% of all data values lie within 3 standard deviations of the mean. So if you subtract 95% from 99.7%, then in these 2 regions, we have 2.7% of the data and dividing that in half, we have about 1.35% in each of those areas. Okay, and then you can combine those as needed. So let's say we wanted to know what percent of the data was below this point. Okay, well then that would be all but 1.35% of the data from here to here. Okay, but then we also have to take into account how much of the data would be more than 3 standard deviations away from the mean. All right, so we have 99.7% of the data within 3 standard deviations, which means we have 0.3% outside of that range. All right, and that would be 0.15% either below 3 standard deviations or above. Let me make that's a decimal, 0.15% and 0.15% above 3 standard deviations away. All right, so the total percentage of data that is below this point, the 2 standard deviations line, okay, that would be 100% minus 1.35% and minus 0.15%. Right, so from here down would be about 98.5% of the data. All right, so let's look at an example. A survey finds that the prices paid for 2-year-old Ford Fusion cars are normally distributed with a mean of $17,500 and a standard deviation of $500. Let's consider a sample of 10,000 people and then answer some of these questions. All right, so let's draw a picture. We'll draw a normal distribution, and the mean is 17,500, and then a standard deviation of $500. So 1 standard deviation away would be 18,000, and 1 standard deviation below the mean would be 17,000. Okay, 2 standard deviations above would be 18,500. 2 below would be 16,500. All right, 3 below would be 16, and 3 above would be 19. Okay, so the first question, how many people paid, this is a typo in the ebook, so how many people paid between 17,000 and it should be 18,000. Okay, so we're looking at this range right here, right? And you'll notice that that's from 1 standard deviation below the mean to 1 above. So that rule would tell us that 68% of people fall in that range, and then 68% of 10,000 is 6,800. All right, how many people paid less than 17,000? So that would be from here down. Okay. So a couple ways you can find this. We could add up all of these percentages that we already found, right? Or you could also notice that the green represents 68% of the people. So that means that the other 32% are either more than 1 standard deviation away from the mean in either direction. Okay, so the purple lines here represent 32% of the people, and if you divide that in half because it's symmetric, that means that 16% of the people are going to be below 1 standard deviation away from the mean. All right, so that's 16% of 10,000 people, which is 1,600. Okay, and then finally, how many people paid more than 19,000? So that would be more than three standard deviations above the mean. All right, well, we know that 99.7% of people fall within 3 standard deviations, right, in here. So that means that 0.3% are either more than 3 or less than 3. And then if you cut that in half, that would mean that 0.15% of everyone would be up here paying more than 19,000. All right, so 0.15% as a decimal is 0.0015, and then that times 10,000 would give you 15 people. So this is consistent with what we know about the spread of the data. We should see very few people that are paying above 19,000 or below 16,000, since this is a normal distribution. Now in this example, we've only dealt with prices that were exactly above exactly 1 standard deviation or 2 or 3, but let's say we wanted to know how many people paid more than 20,000 or less than 14,500, right? Things that don't exactly fall on those standard deviations. So if we wanted to find that, that's the point of a z-score or a standard score. It tells us how many standard deviations above or below the mean any particular data value is. So we find that z-score by finding the data value's deviation. So you can take the data value and subtract the mean, right? And then we divide that by the standard deviation. All right, so let's say that the standard deviation is 500, as in the last example. All right, and let's say that our price, so let's go with like 20,000. All right, well, how far above the mean is that? Well, the mean was 17,500. Oops. Okay, so that means that 20,000 is $2,500 above the mean. That's its deviation. And then dividing that by the standard deviation of 500, right, gives us 5, which means that that price is, we can almost say it's like 5 chunks of $500 above the mean. And I happen to pick a nice number here with 20,000, but this would work if we did 21,000 or $21,352, and then we would get pieces of $500 above the mean. It might be like 5.2 deviations away from the mean. So let's look at another example. The Stanford-Binet IQ test is scaled so that its scores are normally distributed with a mean of 100 and a standard deviation of 15. All right, let's find the standard scores or z-scores for the IQ scores, which are on a different scale, 85, 100, and 125. Okay, so for the score of 85, we take that data value and we subtract the mean, which is 100, and divide by the standard deviation, which is 15. Okay, so its deviation is negative 15. All right, because that score is below mean. And how far below the mean is it? Well, it's exactly 1 standard deviation below the mean. So its z-score is negative 1.00. A score of 100 is exactly on the mean. All right, so its deviation is 0. And 0 divided by 15 is 0. So its z-score is 0. And then a score of 125 is above the mean by 25. Okay, and then 25 divided by 15 tells us that score is about 1.67 standard deviations above the mean. Okay, so it's between 1 and 2 standard deviations above the mean. Another way to describe where a data value is in the normal distribution is to find its percentile. All right, so if we look at the normal distribution, and here's the mean, and if we look at data values that are exactly 1 standard deviation above the mean, okay, then we know exactly what percentage of data is below that data value point, since we have that 68, 95, 99.7 rule. Okay. However, if we had a data value that's somewhere between the mean and 1 standard deviation away, okay, then we can't necessarily use that rule, the 68 rule, to predict exactly what percent of data is below that point. right? However, if we had a scale that could convert z-scores into percentiles, then we would know this exactly. All right, so there is a calculation that does this. You can find this in Excel. There are online calculators, or you can also use a table, something like this. This is in your reading, to convert z-scores into percentiles. Okay, so a z-score places the data exactly somewhere on this distribution. All right, like the one we just did that was 1.67 standard deviations, right, away. All right, so here's SD. Okay, so a data value that's 1.67 standard deviations from the mean would have a certain z-score. All right, and we said that its z-score was 1.67. And then if I want the percentile, all right, or what percentage of the data is less than or equal to that data value, then I would go to this chart and I would find the z-score. And I know this is a little bit small to read, so you can find this in your textbook, but 1.67 is between these two z-scores, okay? And then we can see that it's in the 95th percentile roughly. Okay, so about 95% of the data is below that point. Okay, so let's look at an example. If we want to go back and forth between percentiles and standard deviations, we can do so using those z-scores. All right, so let's say we know cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. All right, so let's draw this. You don't have to do this, but I like to see the picture. Okay, so the mean is 178. And then we have a standard deviation of 41. So one standard deviation above the mean would be 219. And one below would be 137. Okay, and I'll stop there for now. But we want to know in what percentile is a 20-year-old man with a cholesterol level of 190. Okay, so he's going to fall somewhere right around here in the data, okay, with a cholesterol level between 178 and 219. All right, so exactly where between those 2 points? Well, let's find his z-score. Okay, so we take his data value, 190, and we subtract the mean, and we get 12. Okay, and then divide that by the standard deviation, which is 41. And we get about 0.29. Okay, so he's about a third of a standard deviation above the mean. Okay, so that's the z-score. Z-score. And then we can go to our chart and find the corresponding percentile. Okay, so 0.29 is just about 0.30, and the percentile that corresponds with that is 61.79, and that's fairly close to the 62nd percentile. All right, so that would mean that about 62% of men ages 18 to 24 would have cholesterol levels lower than 190. Okay, next question. What cholesterol level corresponds to the 90th percentile, which is the level at which treatment may be necessary? So we'll look at our chart and let's convert to a z-score. So we find the 90th percentile, and that's fairly close to a z-score of 1.3. Okay, and that z-score means that whatever cholesterol level that corresponds to is 1.3 standard deviations above the mean. All right, so 1.3 times the standard deviation of 41 is 53.3. Okay, so if we're looking at his cholesterol level, we would start with 178, okay, the mean, and then add 53.3. All right, or even just 53, and that's about 231. All right, so a cholesterol level of 231 up here somewhere. Okay, that means that 90% of men ages 18 to 24 fall below that level, right? And then a cholesterol level of 231 is the level at which treatment may be necessary. All right, two comments about percentiles. First of all, notice that these are comparing to a sample or a population. All right, so you can see it with the cholesterol levels, 90%. It doesn't mean that he has 90% of the possible cholesterol level. That's not quite what this is saying. It's comparing him to the rest of the people in this distribution. Okay, so percentiles are for comparison. The second thing to notice is that this chart doesn't show all of the z-scores and percentiles, so we were just estimating and getting pretty close to the z-score that we wanted. If you used an online calculator or the tool in Excel, this would give you a more exact calculation for these things.